Properties of matrix multiplication. Hello, everyone. To begin, let's reflect on our previous lessons. We have already established that matrix multiplication is a unique operation, and it behaves quite differently from the multiplication of real numbers that you are already familiar with. One of the most critical distinctions you must remember is that matrix multiplication is generally not commutative. In other words, if you multiply matrix A by matrix B, the result is typically not the same as multiplying matrix B by matrix A. To put it simply, A times B does not equal B times A. However, while the commutative property does not apply, there are several other algebraic properties that matrix multiplication does satisfy. These properties are essential tools for us. They allow us to simplify complex matrix equations and perform algebraic manipulations with confidence. In the upcoming slides, we will explore these properties in detail, starting with the associative law. 1. Associative law. Now that we have established that matrix multiplication is not commutative, let's move on to the properties that actually do hold true. First, we have the associative law. This law states that when you are multiplying 3 or more matrices, the way in which you group them using parentheses does not change the final result, provided that the order of the matrices remains exactly the same. To put this into a formal definition, if we have matrices A, B, and C, and the products are defined, then the product of A and B multiplied by C is equal to a multiplied by the product of B and C. Let's break this down step by step to ensure there is no confusion. First, you must maintain the sequence. The order of the matrices must stay as A, then B, then C. As we mentioned in the previous slide, you cannot swap their positions. Doing so would violate the rule of non-commutativity. Regarding the grouping, you have two options. You can first multiply matrix A and matrix B, and then multiply that resulting matrix by matrix C. Alternatively, you can change the grouping and first multiply matrix B and matrix C, and then multiply matrix A by that result. The key takeaway here is that both of these methods will yield the exact same resulting matrix. To see this in action, we will walk through a concrete numerical example in the next slide. Example of associative law. First, let us define our three matrices. Matrix A is a row matrix containing the elements 1 and 2. Matrix B is a column matrix containing 3 and 4. And matrix C is a simple 1-by-1 matrix containing the value 5. Our goal here is to verify the associative law by checking if the product of A and B multiplied by C is equal to a multiplied by the product of B and C. Let us begin with the first grouping. In step 1, we calculate the product of A and B. We multiply 1 by 3 and add it to 2 times 4. This gives us 3 plus 8, resulting in a 1-by-1 matrix containing 11. In step 2, we take this result and multiply it by matrix C. Multiplying 11 by 5 gives us a final result of 55. Now, let us test the alternative grouping to see if the result remains the same. In step 3, we calculate the product of B and C first. Since B is a 2-by-1 matrix and C is a 1-by-1 matrix, we multiply each element of B by 5. This results in a column matrix containing 15 and 20. In step 4, we multiply matrix A by this result. We take 1 times 15 and add it to 2 times 20. This gives us 15 plus 40, which equals 55. As you can see, both methods of grouping yielded the exact same result of 55. This successfully verifies the associative law. Now that we have defined the associative law, let us look at a concrete example to see how it works in practice. Keep in mind that while we can change the grouping using parentheses, we must never change the sequence of the matrices. We will revisit this point when we discuss common mistakes later in the session, but for now, let us proceed to the distributive law. 2. Distributive law. Now that we have explored the associative law, let us move on to the second major property, the distributive law. Just as you have seen in basic algebra with real numbers, matrix multiplication distributes over matrix addition. However, because we established in our first slide that matrix multiplication is generally not commutative, we must be very precise about the order of multiplication. Consequently, this property exists in two distinct forms: distribution from the left and distribution from the right. Let us examine the formal definitions. Provided that matrices A, B, and C have compatible dimensions for these operations to be performed, we have two laws. First, the left distributive law states that matrix A times the quantity B plus C is equal to matrix A times B plus matrix A times C second. The right distributive law states that the quantity A plus B times matrix C is equal to matrix A times C plus matrix B times C. To ensure you have a clear, step-by-step understanding, let us break these down. Regarding left distribution, if a matrix A is multiplied by the sum of two matrices, B and C, it is equivalent to multiplying A by B and A by C separately, and then adding those two resulting matrices together. Notice that matrix A remains on the left side in both terms. Similarly, for right distribution, if the sum of two matrices, A and B, is multiplied by a matrix C from the right, it is equivalent to multiplying A by C and B by C separately, and then adding them. Here, matrix C must remain on the right side of both terms. In the next slide, I will provide a real-world analogy to help you better visualize how this distributive process works in a practical scenario. Real-world analogy for distributive law. Now, to help you better visualize the distributive law we just covered in the previous slide, let's look at a real-world analogy. Imagine a company that operates two different branches, which we can refer to as branch B and branch C. Each of these branches produces different quantities of items. Now, suppose there is a tax rate or a scaling factor, represented by matrix A, that needs to be applied to the company's production. If we apply this factor, matrix A, to the combined total production of both branches, which is mathematically equivalent to multiplying matrix A by the sum of branch B and branch C, it is exactly the same as applying that tax to branch B and branch C individually first, and then summing those two totals together. Essentially, this illustrates that multiplying a matrix by the sum of two others is the same as multiplying them separately and then adding the results. Once you have a firm grasp of this distributive property, we will move forward to discuss the multiplicative identity in the next section. 3. Multiplicative identity. To understand this concept, let's first recall a basic rule from real number algebra. You know that the number 1 is considered the multiplicative identity because any number, let's call it x, multiplied by 1 simply equals x in matrix algebra. This same role is played by a special matrix called the identity matrix, which we denote with a capital letter I. So, what exactly is an identity matrix? An identity matrix is a square matrix where all the elements along the principal diagonal, which is the diagonal running from the top left to the bottom right, are ones, while all other elements in the matrix are zeros. For example, a 2x2 identity matrix consists of ones on the main diagonal and zeros in the other two positions. To put this into a formal definition, for every square matrix of order n by n, there exists an identity matrix I of the same order such that I times A equals A, and A times I also equals A. Let's break this down step by step to ensure a clear understanding. First, we must consider compatibility. The identity matrix must be of the same order as matrix A for the multiplication to be mathematically defined and for the result to be matrix O itself. Second, if we perform left multiplication, meaning we multiply matrix A by the identity matrix I on the left, the matrix O remains completely unchanged. Similarly, if we perform right multiplication, multiplying matrix A by the identity matrix I on the right, the result is again the original matrix A. Now that we have explored the associative and distributive laws, let's move on to the third important property, the multiplicative identity. In the next slide, we will walk through a practical example to see exactly how this works in a calculation. Example of multiplicative identity. First, let us define our matrices. We will use a general 2x2 matrix, which we will call matrix A, containing the elements A, B, C, and D. Alongside this, we have the 2x2 identity matrix, denoted as I, which consists of ones on the main diagonal and zeros in the remaining positions. Let us proceed to step 1, where we calculate the product of matrix A multiplied by matrix I. When we perform the multiplication, we multiply the rows of A by the columns of I. For the first row, we calculate a times 1 plus B times 0, and a times 0 plus B times 1. For the second row, we calculate C times 1 plus D times 0, and C times 0 plus D times 1. As you can see, once we simplify these expressions, the result is a matrix with the elements A, B, C, and D. This confirms that A times I equals A. Now, let us move to step 2 to see what happens when we multiply in the reverse order. Matrix I multiplied by matrix A. In this case, we multiply the rows of the identity matrix by the columns of matrix A. This gives us 1 times A plus 0 times C, and 1 times B plus 0 times D for the first row. For the second row, we have 0 times A plus 1 times C, and 0 times B plus 1 times D again. After simplifying, we find that the resulting matrix is exactly our original matrix A. Now that we have established the theoretical definition of the multiplicative identity in the previous slide, let us look at a concrete example to see how this works in practice. This example demonstrates that the identity matrix acts just like the number 1 does in basic arithmetic. Whether you multiply from the left or the right, the original matrix remains unchanged. Keep this result in mind, as in the next slide, we will discuss some common pitfalls, specifically why you should not assume this kind of flexibility applies to all matrix multiplications. Common mistakes to avoid. First, let's discuss the danger of confusing associativity with commutativity. A frequent error is for students to assume that because the associative law allows us to group matrices differently, meaning the product of A times B, then multiplied by C, is the same as A multiplied by the product of B and C, they can also change the actual order of the matrices. For instance, some might mistakenly think that A times B is equal to B times A. Please remember, while you are permitted to change the grouping using parentheses, you must never change the sequence of the matrices. Next, we have the issue of incorrect distribution. When applying the distributive law we discussed earlier, a common mistake is to write that A times the sum of B and C is equal to A times B plus C. This is incorrect. You must always remember that the matrix A must be distributed to every single term inside the parentheses, meaning it must be multiplied by both B and C. Finally, let's talk about identity matrix dimensions. As we saw in our previous examples, the identity matrix acts as the multiplicative identity, but its size must be compatible with the matrix it is multiplying. If matrix A has m rows and n columns, then for the product of I times A to be defined, the identity matrix I must be a square matrix of size m by m. Conversely, for the product of A times I to be defined, the identity matrix I must be a square matrix of size n by n. Now that we have covered the primary properties, let us address some common misconceptions to ensure you avoid these pitfalls in your calculations. Keeping these 3 warnings in mind will help you maintain accuracy in your algebraic manipulations. Now, let us move to the final slide to summarize the key takeaways of this lesson. Key takeaways. First, let's revisit the associative law. As we demonstrated in our earlier example, the product of A and B, then multiplied by C, is equal to A multiplied by the product of B and C. The most critical point to remember here, which we highlighted in our common mistakes section, is that while the grouping of the matrices using parentheses does not change the result, the sequence of the matrices must remain exactly the same. Next, we have the distributive law. This property confirms that matrix multiplication distributes over addition. Specifically, A times the quantity B plus C equals A B plus a C, and similarly, the quantity A plus B times C equals A C plus BC, just as we discussed with our real-world analogy of the company branches. remember that the matrix must be distributed to every single term inside the parentheses. Finally, let's summarize the multiplicative identity. We have learned that I times A equals A times I, which simply equals A in this context. The identity matrix I acts exactly like the number 1 does in regular scalar multiplication, leaving the original matrix unchanged. All right, let's wrap up everything we have covered in this session by reviewing the key takeaways. Keep these 3 properties in mind, as they will be essential for simplifying more complex matrix equations in our upcoming lessons.